Hello everyone, welcome back to another discussion in dynamics. Today we will continue talking about kinematics of rigid bodies, and today we will focus on acceleration analysis. And plan for today is following. We will start with a very brief lecture review, and then we will do two examples. Without further ado, let's start our discussion. So here is my brief lecture review. I would like you to imagine that we have a rigid body of arbitrary shape. So let's say, I don't know, such shape. Is this arbitrary? Yeah, one of them has to be arbitrary. So let's say that this one is arbitrary. Okay, so anyway, this is rigid body. And we know acceleration of this point. Let's say point A. Maybe. We know that value. We know that vector, and also we know a couple of more things. We know, let's assume that we know omega of the body. We also know alpha of the body, where omega and alpha, of course, refer to angular velocity and acceleration, respectively. And we will know one more thing, but I will mention it in a second. So these are our norms. We know AA, we know omega, and we know alpha. And the question is, what is acceleration of this point? Can we figure out acceleration of this point? Point B. And in order to do that, we need to know one more thing. Namely, we need to know geometry of this that is in the system. And by geometry, I mean what is the relative position between A and B. So we also must know this vector, RBA. So this guy is also known, RBA. All right, and if we know these four things, we can find AB using following expression. AB is AA plus alpha body times RBA. And in planar motion, the last term is following, minus omega body squared RBA. This is expression for acceleration analysis in planar motion only. In general, so by planar motion, I mean 2D motion, yes? In 3D, that expression looks a little bit different. But we just, in this semester, we focus on 2D motion. So we are just going to use this equation this semester. And today we will use it 5 times. So prepare yourself for that, okay? Any questions? I don't see any questions, so what? So let's do example number 1. Yeah. Okay. Here is example number 1. As usually, please take a couple of seconds to read and understand the problem statement, and also familiarize yourself with the geometry of our system. Okay, so what do we have in here? We have following mechanism that is presented in the picture. That mechanism consists of 3 segments. So we have link AB, we have link BC, and we have link CD. I believe we know everything about its geometry because we know parameter L. L is 2 meters, plus the configuration of our system is presented in the picture. Additionally, they told us that omega and alpha of the AB segment are 10 radians per second and 300 radians per second square, respectively. And they ask us to find alpha of this segment. So they ask us to find alpha BC. And they also ask us to find alpha CD. These are not known angular accelerations. And I think I would like to say right now the most important part of today, that the two knowns that are currently in the green box, so these guys, omega BC and omega CD, does not have to be provided to us in order to solve that problem. Okay, so these guys, we do not have to know them before we start solving that problem. Because even though we are asked to find angular accelerations, alpha BC and alpha CD, it does not mean that we should jump straight into acceleration analysis, yes? Sometimes we must run velocity analysis first, where we will find values for omega BC and omega CD. Okay? I ran that velocity analysis yesterday just to speed up our discussion, yes? And I just do not want this discussion to last 2 hours. Okay? So I just ran our velocity analysis yesterday in the evening, and these are the values I obtained. So let's assume that our omega BC and omega CD are known. And now I think that we know every single parameter before running our acceleration analysis. Also, if you would like to see how to run velocity analysis, please watch the previous video. Yeah, so not this one, but the previous one. We focused on velocity analysis there. Okay, I have a strange feeling that I'm talking too much. So maybe without much talking, let's start the solution. Yes, yeah, let's do it. So this is my solution. And our goal is to find alpha BC and alpha CD. Okay, so I'm just going to run acceleration analysis between 2 points. Let's say between points B and A. So I will start with writing down the expression from the previous board. So AB is equal to AA plus alpha AB times RBA minus omega AB squared RBA. Okay, first question to you. What is acceleration of point A? What is AA? What is acceleration of this point? It is 0 because A is fixed. Exactly. So our AB will be following. 0, 0, alpha AB is given. Does alpha AB rotate in a positive or negative direction? I think it's negative. So it will be minus 300 cross this vector. Okay, I must draw that vector in the board. So let's say that it will be orange, okay? That orange vector is RBA. And based on the picture, its components are 0, L0 minus omega AB squared and omega AB is 10, and does it rotate in a positive direction or negative? Positive. 10. Actually, it doesn't matter because we are going to take a square of it anyway. And in here, exactly the same vector. Okay, so if you solve this determinant, you will obtain following expression. In here, you will just have 300L. 300L, 0, 0. I solved it yesterday. Okay, so let's put everything into one bucket. Our AB is equal to 300L minus 100L. And L is 2 meters, so our AB is 600 minus 200 meters second squared. Okay. Any questions to what happened on the board? Okay, so all of a sudden we know acceleration of point B. Let's move forward. Yeah, let's move along our linkage. Now let's focus on acceleration analysis between C and B. I will copy that drawing here, okay? I like to have that drawing on the board. Let's say here. Okay, so I want to write down this expression. AC is equal to AB plus alpha BC times RCB minus omega BC squared RCB. Okay, guys, and let's fill out that expression. AC is not known. AB we just found, so this will be 600 minus 200, 0. Alpha BC is not known, so let's just assume that it rotates in a positive direction, okay? So this will be 0, 0 alpha BC. Yeah, and I assumed in here, even if you look at the drawing, I assume that our alpha BC rotates in a positive fashion. We will see if at the end, we will see if my assumption is correct or not. Cross this vector. Okay, and this vector is not on the board. I must draw it. And this will be the horizontal one. So R, this guy is RCB. And since it's horizontal, I believe that its components will be L, 0, 0. Okay, minus square L, 0, 0. Okay, and omega BC, I obtained yesterday, right? Omega BC is 10 clockwise, as you can see in here. So it will be minus 10 in here. But it doesn't matter if it's minus or plus. It's squared anywhere, anyway, yeah? So that minus doesn't matter. And now you can see why velocity analysis is important, yes? Because without running velocity analysis, we would not know this parameter. Do you see that? Yeah? That's why, unfortunately, before running acceleration analysis, we must run velocity analysis because we do not know omega BC. Cool. Okay. So let's continue with our solution. If you solve this determinant, and I did it yesterday, you will obtain here 0, alpha BC, L, and 0. Okay. So now let's put everything into one bucket. Our AC is equal to 600 minus 100 L, and in here we'll have minus 200 plus alpha B C L 0. Plug in values and obtain that our AC is equal to 400. And in here we will have minus 200 plus 2 alpha BC 0. All right, I think we are done with this acceleration analysis. And this is as much as we can squeeze from our acceleration analysis. I hope that you can see it. Yeah? We didn't obtain numeric value because this guy is not known. Alpha BC is unfortunately not known. Yeah, but in order to solve for it, we must run one last acceleration analysis, yes, between the remaining pair of points. So let's do it here. Let's run accel analysis between D and C. So again, I will start with writing that magical equation from the previous board. So this will be AD is equal to AC plus alpha CD times R DC minus omega CD squared R DC. Okay, and let's fill out that equation right now. So, question to you. What is acceleration of AD? Exactly. For the same reason as earlier, yeah? Point D is fixed. So this guy is 0. And we can write in here 0, 0, 0. That is equal to AC. AC we found in the previous step. So in here I'm gonna write 400 minus 200 plus 2 alpha BC 0. Okay. Plus that alpha, but we don't know that alpha, yes? So let's again assume that it rotates in a positive fashion. 0, 0, alpha CD. Oh, and that guy. I must draw that guy. I'm gonna use green for it. Okay. So this green vector is R DC. And based on the picture, its components are L minus L 0 minus something squared L minus L 0. So omega CD was 10, but I forgot if it's clockwise or counterclockwise. Let me scroll up the board. Omega CD is counterclockwise. So it will be plus 10. But again, it doesn't matter because it's squared anyway. Okay, guys. Okay, let's follow our recipe. So let's solve this determinant. And if you solve it, you should obtain alpha CD, L, alpha CD, L, and 0. And now let's put everything into one bucket. So we will end up with 0, 0, 0. That is equal to 400 plus alpha CD L minus 100L. And in here we will have minus 200 plus 2 alpha BC plus alpha CD L plus 100L. I hope I didn't make any mistake. Yeah, let's plug in values and let's see what we will end up with. So in here we will have, I believe, 200 plus 2 alpha CD. Just keep in mind that L is 2. And I think that in the second equation, this minus 200 will cancel out with this 200. I believe so, because L is 2. So in here, we will just end up with 2 alpha BC plus 2 alpha CD. Great. So I think we ended up with two equations and 2 unknowns. Yeah, we have equation in the x component, and we have equation in the y component. So let's solve it quickly. So we will have 0 that is equal to 200 plus 2 alpha CD, and we also will have 0 that is equal to 2 alpha BC plus 2 alpha CD. Clearly, 2 equations and 2 unknowns, because this is not known and this is not known. Okay, let's solve it. So our alpha CD is equal to minus 100 radians per second square, and vector-wise, our alpha CD is equal to minus 100 K radians per second square. Or if you like my favorite notation, you can just write 0, 0, minus 100. Oh, minus 100. Radians per second square. Okay, and alpha BC, if you solve that, it will be equal to 100 radians per second square. And vector-wise, it will be just 100 K radians second square. Okay, so it seems to me that this guy rotates clockwise, and this guy rotates counterclockwise. Yeah, I think that's the end of the example. Any questions? No questions? Who is confused? Of course, besides me, but I'm confused most of the time, actually. But you can get used to it, actually. Yeah. Okay, guys. So I hope that you can see that it is very repetitive, yeah, and we can just automate that process, yes? Cool. Joey, I see that you raise your hand, yeah.
So, for acceleration, is that just standard clockwise? It's negative and counterclockwise. Is that like the right hand rule?
Yeah, exactly. Yeah. I'm not sure if we have time for me to explain that. Yeah. Maybe if we have some time, I can tell you why. Yeah. But anyway, this is the standard. Yeah. Clockwise is negative, counterclockwise is positive. Yeah. And you can see the directions that they are rotating. Yeah. Counterclockwise, that means that our body rotates this way. Yeah. And clockwise is this way. I mean, I'm saying that you know that. Okay. I'm sorry, Joey. So what now? Any other question or example number 2? Okay, example number 2. So we will start exactly in the same way as usually. Please familiarize yourself with the problem statement before we start our solution. Alrighty. So what do we have in here? We have three bodies. We have link AB. We have link BD. And we also have body D. And our body D is constrained. Yeah. Our body D can only move in a horizontal direction. it cannot move in the vertical direction. In other words, this is the trajectory of point D. Yes? Trajectory D. Okay, what do we know in here? Obviously, we know geometry. We know that L1 and L2 are equal respectively to 3 and 8 inches. We also know that at this time instant, the configuration is presented here in the picture. To be more specific, at this time instant, theta is 40 degrees. Okay? In a second, it will have a different value, yes? But in this course, we focus on what is happening right here, right now. We don't care what will happen in a second, okay? Problems in this course are solved for that particular configuration given to you and that particular initial conditions. And by initial conditions, I mean velocity field. So at this time instant, our omega AB, so omega of this segment, is 200 RPMs, 200 revolutions per minute, which is useless unit for us. That's why we must convert it into radians per second. What is exactly presented in the board? Yeah? So in case you are wondering how to go from RPMs to radians per second, please follow the procedure that is on the board. I did it yesterday. What do they ask us for? Oh, one more information. This is constant. Yeah, that omega AB is constant. And what do they ask us for? They ask us to find what is angular acceleration of the other link. Yeah, they ask us to find what is alpha BD. This is not known. And also they ask us to figure out what is acceleration of this point D. So we are just going to find these two vectors. And again, I hope you don't mind if I repeat myself from like 20 minutes ago. That problem can be solved if these two parameters are not given to you in the problem statement. Okay, these parameters that are just covered with that blue doodles. Yeah. So the omega BD and beta, they don't have to be given to you in the problem statement. Yes. In order to find them, you must run velocity analysis before running the acceleration analysis. I did it yesterday. These are the values I obtained, okay? We are going to use these two parameters in our acceleration analysis, yes? It was necessary for me to run velocity analysis before running acceleration analysis, yes? Because I need to know these two parameters. Is that clear? It is. I see that it is, and I see that you're impatient. So let's start. I don't want to make you nervous or angry at me, so let's start solution. Okay, sorry. This is my solution. I am going to start with acceleration analysis between A and B, if you don't mind. Between B and A. So I'm just gonna follow the procedure. Yeah, I'm just going to start with this expression. AB is equal to AA plus alpha AB times RBA minus omega AB squared RBA. Okay, guys, two questions for you. What is acceleration of point A? Point A is here, by the way. Nobody said anything. That means that everybody knows that. It's 0, yeah, because point A is fixed. And how about acceleration alpha AB? What can you tell me about this acceleration? Why? Yeah, constant is, doesn't matter if it's clockwise or not. If it's constant, if velocity is constant, that means that angular acceleration will be 0. Perfect. So this is also 0. Oh, sorry. This is also 0 because our omega AB is constant. Okay. Okay. So thanks to you guys, our problem is simplified tremendously because now our AB has only one component right now. It will be minus minus 209.44 squared times this vector. Okay, I need that vector. Let me use green maybe to draw it. So this will be our RBA. And I think that the components of RBA are L1 cosine 40 degrees and L1 sine 40 degrees. Okay, guys, grab your calculators and obtain that our AB is following. It's approximately minus 100,807.88 and minus 84587.850 inches per second square. I will solve that problem in inches, okay? If you want to solve it in feet, just divide these two values by 12. You will have them expressed in feet. Okay. So this is first part of the problem, and the second part of the problem is acceleration analysis between D and B. So we will run that acceleration analysis for one more time, for the final time today, for the 5th time today. Okay, let me copy that drawing. Yeah. So this is our drawing. Okay, so let's write our magical expression from the previous board. So in here we will have AD is equal to AB plus alpha BD times R dB minus omega BD squared RdB. Okay, so first thing to observe in here is that AD moves horizontally. Yes? So I think we all know what is its vertical component. Its vertical component will be 0. Yeah, so we can write in here AD 0, 0. Now, AB we just found, so it will be minus 100,808. Let's round it up. Minus 84588. 0. Okay. Plus alpha BD, we don't know it. We must find it. Cross this vector. Okay, let me draw that vector. It will be again green. Okay, so this guy, this vector is RdB. And its components are, I think, L2 cosine beta. Yeah, and beta, as you can see, I found yesterday. Yesterday in my velocity analysis. So beta is 13.95 and minus L2 sine beta and 0. Minus 62 squared times the same vector. So I'm just going to copy it. So again, guys, I know that you all see it, but I'm just going to say it anyway. You see that running velocity analysis before acceleration analysis is crucial, because we must know that 62, yeah? We must know that our omega BD is 62. And you can obtain it when you run velocity analysis. Okay, I think that's all. So let's simplify our vector expression, yes? Let's simplify our vector expression, and we will end up with, oh, first of all, determinant. Pardon me. This determinant, if you want to solve it, you will end up with alpha BD L2 sine beta alpha BD L2 cosine beta, where of course beta is 13.95. Okay, and now we can simplify our vector expression. So in here we will have AD 0, 0, and in here we will have minus 1, 0, 0, 8, 0, 8, plus alpha BD L2 sine beta minus 62 square L2 cosine beta. And in the second row, we will have 84588 plus alpha BD L2 cosine beta plus 62 squared L2 sine beta, and 0 as a z component. All right, we are almost there. We ended up with 2 equations and 2 unknowns, because clearly we have one equation for the x component and one equation for the y component. We also have the third equation, right? But it's trivial. Z component tells us that 0 is equal to 0. Huh. Great. So we have 2 equations and 2 unknowns, because our unknowns are AD, and I believe that this parameter is not known, alpha BD. Every other parameter in these 2 equations we know. Yeah. So we have 2 equations, 2 unknowns, solvable. And I solved it yesterday at home, and I ended up with alpha BD, that is approximately 9940 radians per second square, and vector-wise it will be 9940k radians per second square. So that means that it rotates counterclockwise, because we obtained a positive value. And the last final thing for today is AD. If you solve it, you should obtain minus 111,482.7 inches per second square. And vector-wise, our AD has only x component, right? So our AD has actually, it looks like that, minus 111,482.700 inches per second square. Okay. Before we go, I just want to say one more thing, but I'm just wondering if are there any questions? How do you like it, guys? Yeah. Do you think you understand acceleration analysis? Yeah. So basically, right now, my advice is, so I think that it's, you see the procedure there, yeah? There are some steps you should follow in order to solve it, yeah? So my advice is that just solve homework problems with knowledge you just learned today, okay? And then you should probably destroy quiz 5 probably, and also 1 question on the exam, yeah? Points for free, in other words, yeah? Yeah, and before we go, I want to say one more thing. You can see that this is very repetitive, yeah, procedure, yeah, and kind of dull, yeah. That's why we don't do this. We just have our computers to do it for us, yes. So probably in this course, maybe some other courses at the university, you will be asked to do it with pen and paper, yes. However, in real life, we use our computers to do it, yeah. So basically, they do all of these calculations for us. Yeah, so now at least you know what happens behind the scene. Your job as an engineer will be following. You will just have your engineering software and you will just set up that problem. So you will basically, yeah. Guys, can you please not make noise right now? Thank you, yeah. So basically your job as an engineer will be to set up that problem. So basically provide geometry to the computer. So you will basically have to draw that system, yes, using some, I don't know, SolidWorks or NX. And then you just, once you have the geometry, you will just have to set up initial conditions. In this case, it's omega IB equal to 2000 RPMs. Once you provide that information to the computer and press enter, probably, computer will give you these values. Okay, plus these values as well. Yeah, so the point of today's discussion was just to show you what happens behind the scene, what your computers are actually doing. Okay, and let's finish on that positive note. Thank you for today. See you next time. Bye-bye.